Welcome back. In today's tutorial, we are creating an intelligent document assistant. I'll show you step-by-step how to maintain your files in a Chroma vector database and build a seamless pipeline so you can query your knowledge base directly through Claude Desktop. By the end of this video, you'll have a fully functional, local RAG setup ready to go. Do you have any document in the Chroma DB? Yes, we get a response with the details of the document. This was the project plan PDF document loaded in the Chroma DB. This is the Python script, which is waiting for any document in the staging folder and uploads the document to the Chroma DB using the document details in the JSON file. Let us break down the technical architecture step by step. The ingestion pipeline. We take files, PDFs and text docs from a local staging folder and use a Python script to vectorize and load them. Chroma vector database. We utilize Chroma DB, running locally, to store and index your document embeddings securely. Claude Desktop plus Gemma 4. We connect the Claude Desktop interface to the open-source Gemma 4 LLM via the Model Context Protocol, or MCP. Local RAG. When you ask a question, the MCP queries Chroma DB for context before the model answers, giving you local, private, context-aware responses. Tech stack used for this project. Docker. Chroma DB is running as a Docker container in the local machine. Ollama is the local LLM runner and engine. Gemma 4, Google's latest state-of-the-art family of open models. Claude Desktop is the user interface UI. Chroma DB is the open-source vector database. FastMCP is the MCP integration framework. Python, the core language used to drive the entire project. Check the link to the README document in the description. It gives step-by-step instructions to install the tools and run this application. Let us load a document and do some testing. Make sure Chroma DB Docker container is running. Let us load this Angel's Supermarket annual performance report. We will update the manifest details for this document and start the docsync process. This document was split into 6 chunks and loaded into the Chroma vector database. Let us give some prompts to query the document. What was the sales of fruits and vegetables in the month of April 2025? Let us compare with the document. Yes, the answer is correct. Let us ask one more question. What was the operational notes for the month of December 2025? We got the right answer of holiday inventory turnover maximized operational capacity. Let us remove this document from the vector database. Change the action in the manifest file as delete. The docsync process detected the change and remove the document. Let us double check the database. Give a prompt. Do you have any document in Chroma DB? We don't see the document. Angel's Supermarket annual performance report. It is deleted. This AI knowledge base works as expected. Target configurations. Sets up global connections pointing to your local services, Chroma DB running inside Docker on port 8000 and Ollama running locally on port 11434. Client handshakes. Connects to the Nomic embed text model via Ollama to generate vector embeddings and instantiates an HTTP client connection to the central Chroma collection, local_knowledge_base. Extension routing. Inspects the file extension of target documents. Format parsing. Dynamically assigns the correct LangChain parsing utility, PyPDF loader, text loader, or unstructured markdown loader, to handle different file types natively. Targeted purging uses Chroma's metadata filter where equals source_ID, doc_ID to find and remove all chunks belonging to a specific document ID. Idempotency safeguard prevents orphan text chunks or duplicate data from remaining in the database when files are updated or removed. Text chunking loads a document and breaks its text into manageable blocks of 1,000 characters with a 150-character overlap using a recursive character text splitter. Metadata tagging injects key identifier tags, source_ID, description, file_path, directly into every individual chunk's metadata payload so downstream apps like Claude Desktop can read and reference them. Atomic replacement clears out old chunks belonging to the document ID first, then calls vector_store.add_documents to generate new embeddings via Ollama and store them inside Docker. JSON processing parses manifest.json safely. It includes a built-in time.sleep 0.5 debounce delay to ensure your text editor has completely finished saving the file to disk before reading it. Action routing loops through the entries in the manifest array and executes the requested operation based on the action tag. Add or update $\right arrow triggers data chunking, metadata injection, and embedding creation. Delete $right arrow purges document vectors from the database entirely. Event interception implements a watchdog system loop that monitors your working directory. It completely ignores general directory changes and specifically fires only when manifest.json is modified and saved. Continuous execution runs an initial sync pass upon script startup to catch any missed updates, then initializes a non-blocking background observer daemon to monitor the file system indefinitely until a manual exit, Ctrl+C, is signaled. Now let us review the MCP Chroma server script. FastMCP instance setup. The script instantiates an MCP Model Context Protocol server named Local Vector DB Search using the FastMCP framework. This acts as the bridge that allows Claude Desktop to recognize and call local custom tools. Embedding model configuration. It connects to the same local Ollama instance, http://localhost 11434, using the Nomic embed text model to process natural language queries into matching vector coordinates. Dockerized database handshake. It initializes an HTTP client pointing to localhost 8000 to establish a persistent connection with a shared local_knowledge_base Chroma collection. This allows concurrent search querying, even while your separate background script updates or deletes entries. MCP decorator. At mcp.tool, the function query_local_documents is registered directly as an executable tool for the LLM. Semantic docstring instruction. The explicit docstring acts as structural prompt guidance for Claude. It instructs Claude exactly when to fire the tool, e.g., when a user asks questions regarding reports, local policies, or uploaded guides. Vector matching. When Claude invokes the tool with a textual search phrase, vector_store.similarity_search, queries Chroma to find the top matching context blocks, defaulting to the top $K equals $4 closest results. Metadata extraction. The script extracts the stored payload properties, source_ID, description, file_path, embedded with each text chunk. String compilation. It packages these components cleanly into formatted context blocks separated by markdown rules, context segment, and joins them into a single coherent text chunk to stream directly into Claude's prompt window. If nothing is found, it returns a fallback notification string. Standard I/O communication. Under the execution guard, __main__, the server is initialized using mcp.run, transport equals style. This uses standard input-output channels to establish a stable, lightning-fast communication line with the parent Claude Desktop app.
Thanks for watching. Like and subscribe if this video was useful.